Okay, so we're going to talk about transforming a random variable today. In other words, so let's say we have a random variable x, and it has a distribution and so forth, and then I'm going to ask you questions about, like, what's the distribution of 5x look like, or what's the distribution of 5x plus 7 look like. Maybe you take a variable, you multiply it by a number, and then add something to it that's called a linear transformation. Spell it this way, a linear transformation of that variable. Okay, so let's consider an example. Suppose you have young children at home, and then you want to give them baths periodically and so forth. That makes sense. But one of the things that you're concerned about is not making the bath too hot or too cold. Well, it turns out there's devices you can buy that will actually create a bath that's the perfect temperature attached to your faucet and so forth. So there's one company, and they claim that the water that comes out of their device is normally distributed with a mean temperature of 34 degrees Celsius and a standard deviation of 2 degrees Celsius. So this is what's going to happen most of the time when you use a device. And I might be a little concerned about this because other articles I read have said that bath water for a baby should be between, say, 90 degrees. Okay, this is another source, 90 degrees Fahrenheit to 100 degrees Fahrenheit. So the question is, how do these two statements match, and will this machine that produces the bath water according to this distribution give me temperatures in this range, and my baby will be safe? Okay, so the problem we have is we're going to have to take this information, this mean and this standard deviation, and convert them into Fahrenheit. Okay, well, it turns out there is a function which will take a temperature in Fahrenheit and tell you what it is as a function of the temperature in Celsius. It looks like this. Temperature in Fahrenheit equals 9/5 times the temperature in Celsius plus 32. And if you look at this equation, it fits what I described earlier. This is a linear transformation of the temperature in Celsius. The temperature in Celsius has been multiplied by a number, and then it's had a number added to it. That's a linear transformation. Okay, so there are a few rules of linear transformations of random variables. Here's one of them. If you have a random variable ax plus b, and x was the original random variable there, and you can tell it's been transformed, it's been multiplied by a and b has been added to it, then the mean of that random variable is a times the mean of x plus b. So that's not really a big deal. It just says if you know the mean of a random variable and you decide to multiply it by an a and add b to it, just do that to the mean and you'll get the new mean. Standard deviation of ax plus b is a little different. If you give this a little thought, it'll make sense. But what the formula says is it's the absolute value of a times the standard deviation of x. Now what you'll notice is over here on the right, the variable b doesn't seem to be contributing anything to that standard deviation. But if you think about it, if you take every x value and you multiply it by a, then the distance between them is now a times as large as it used to be. However, if I take every number on a list and I add b to it, I'm just shifting them all over by b. But the distance between them doesn't change. So that means they're not any more spread out. So it's going to make sense that this formula would not be affected by what you added to every value. Okay, so what we're going to do is we're going to take our mu Celsius, which in this case, the problem was given to be 34 degrees, okay, and our standard deviation in Celsius, which was given to be 2 degrees, and we're going to convert them to Fahrenheit using that formula. So what do we know? Well, we know that mu Fahrenheit is equal to mu of 9/5 Celsius plus 32. But according to our rule, that's just mu of, now here's the rule I'm referring to, this rule right here. If you look at it, I could just take whatever I multiplied x by, multiply that by the mean, and then add whatever's been added. And that's what happens. So this is going to be, actually let's be careful, it's going to be 9/5 mu Celsius plus 32, or 9/5 times 34 plus 32, which equals 93.2 degrees Fahrenheit. Okay, that's promising. That's between 90 and 100, so I'm happy about that. Okay, and if I want the standard deviation in Fahrenheit, well, that's equal to the standard deviation of 9/5 Celsius plus 32, which according to the formula is the absolute value of 9/5 times the standard deviation in Celsius. That's coming from this second formula here. So you'll notice that only A has an effect on the new standard deviation. The original standard deviation in our problem was 2. So it's going to be 2 times 19/5, which is, I should have said 2 times 9/5. Anyway, that's going to give us 9/5 times 2, 18/5, or 3.6. So now we have a new distribution. What we can say is the distribution of the temperature of the water dispensed by the device is normal with a mean of 93.2 and a standard deviation of 3.6. So now, if I want this, if I'm concerned or I believe what the other article said, if you remember at the beginning of this, we said that it was another article I read that told me that bath water temperature should be between 90 and 100 degrees for a baby to be safe. So I might be interested in knowing how likely is it that this device will produce a temperature between 90 and 100. Well, I can do that because I know this is a normal distribution. I know its mean and standard deviation. So here we go. Draw a little picture of this thing and do this. Here's a normal distribution. Not a great picture, but here's 93.2 in the middle. Standard deviation is 3.6. Okay, and we'll mark 90 over here and 100 out here. And we're going to find that area. Okay, so we need some z-scores, and then we'll look up some things on some charts and be done with it. So here, the z-score is going to be 90 minus 93.2 over the standard deviation of 3.6. And over here, the z-score will be 100 minus 93.2 over 3.6. These turn out to equal negative 0.89 and 1.89, respectively. So now what we can do is we can go to a z-chart and look up those values. And remember, when you look up on the z-chart, it gives you the area to the left. So the area associated with this z-score of negative 0.89 is 0.1867. And the area associated with that z-score of positive 1.89 is 0.9706. Okay, so remember, this gives us the following two areas. We know this area over here is 0.1867, and then we know that all the area to the left is this other number, 0.9706. If I were to subtract those two areas, I would get the desired red area in the middle. If you subtract those, you an answer to this probability at 0.7839. So if I want my baby's bath water to be between 90 degrees Fahrenheit and 100 degrees Fahrenheit, then this device, which produces water normally distributed according to this mean and this standard deviation, is going to do that about 78% of the time. Okay, so I better be careful when I do this because there's over a 1 in 5 chance that it's going to give me water that's either too hot or too cold for my baby.